Now in this part of the video, I will be solving question 5 onwards of May-June 2019, paper 2, variant 1. Question number 5, part A. A loudspeaker oscillates with frequency f to produce sound waves of wavelength lambda. The loudspeaker makes n oscillations in time t. Part 1. State expressions in terms of some or all of the symbols f, lambda, and n for the distance moved by a wavefront in time t. I'll show you that diagrammatically first of all, so that I'll make you understand what it exactly is asking you. A wave usually would look like this, or I'll draw two similar waves. I'll draw three similar waves, and this distance from one crest to the other is your lambda, and this one lambda will represent one wave, and then this second lambda will represent the second wave. So from one crest to the other, this lambda will define one wave. So I'll say that lambda is the distance it moves, but how many oscillations does that take is n, right? So n lambda will be the total distance moved by the wavefront. And since lambda represents distance moved by one oscillation, and in total how many oscillations were there, so n will represent the number of oscillations and lambda will represent the distance moved by a single oscillation. Now time t would be time is basically equal to distance divided by speed, so n lambda divided by speed. Speed in terms of waves is frequency into wavelength, so I'll write f and then wavelength. This wavelength and then this wavelength gets cancelled, so I'll write n divided by f, means number of oscillations divided by the frequency of to produce the sound. Now moving on to the next part, use your answers in part 1 to deduce the equation relating the speed of the sound wave to f and lambda. So speed is equal to distance divided by time. So speed is equals to, we got distance from the first part, which was n lambda, divided by time. What did we get from time? So n divided by f. So our speed of the sound wave in terms of f and lambda would be frequency into lambda. Now part B, the waveform for a sound wave is displayed on the screen of a cathode ray oscilloscope as shown in figure 5.1. So this one box represents 1 centimeter on the x-axis and 1 centimeter on the y-axis. The time-based setting is 0.2 millisecond per centimeter. So one box will now represent 0.2 milliseconds in terms of time. Determine the frequency of the sound wave. So I'll take this. So the formula for frequency is 1 divided by time period. Time period is the total time taken for one complete oscillation. Now we can find the time taken for one complete oscillation from the graph given above. One complete oscillation is one successful crest and one successful trough. So I'll take that from here. This is one complete oscillation. So this one box represents 0.2 millisecond. This also represents 0.2. This also represents 0.2. So this also represents 0.2. This becomes total 0.8 milliseconds. So 0.8 milliseconds were taken to complete one oscillation. So I'll write that over here is equal to 1 divided by 0.8. Now since this is in milliseconds and I should convert that to SI units, so I'll multiply it with 10 to the power negative 3 I'll close the bracket, and our answer will be equal to frequency is equal to 1250 Hz. Never forget mentioning units. Okay, moving on to part C. Two sources S1 and S2 of sound waves are positioned as shown in figure 5.2. Okay, so these are two sound sources. The sources emit coherent sound waves of wavelength 0.85 meters. A sound detector is moved parallel to the lines S1, S2 from a point X to point Y. Okay, so these were the positions taken by sound detector L, Q, L, Q, L. These were the positions. These five were the positions, and these were taken by the sound detectors. Alternate positions of maximum loudness L and minimum loudness Q are detected as illustrated in figure 5.2. Distance S1x is equal to distance S2x, means whatever distance sound wave travels from source 1 until this point is equal to the distance traveled by the sound from the source 2. So this distance is equal to this distance traveled. S2x distance S2y is 7.4 meters, means distance traveled by sound wave from a source to point L is 7.4 meters. Part 1, explain what is meant by coherent waves. So coherent waves are those waves which have constant phase difference, or they have constant path difference. So I'll write that over here. Waves which have constant phase difference, or maybe path difference. Now, second part, state the phase difference between the two waves arriving at the position of minimum loudness Q that is closest to point X. Okay, so this is the point they're asking for over here. What is the phase difference between the sound waves which are traveling from source 1 and source 2? So over here, the phase difference will be equal to 180. Because they say that point L is the maximum points, point L's are maximum points and point Q's are minimum points, and whenever they say that some points are minimum, means the phase difference between the sound waves will be equal to 180. So I'll write that over here. Phase difference between the waves is 180 degrees. Now part 3, determine the distance S1y. Now S1y, distance S1y. Okay. This is what they're asking, S1y. The distance traveled by the sound wave from source 1, you have to calculate that distance. Now to calculate that distance traveled by the sound wave from source 1 to L is equal to the distance traveled by the sound wave from source 2 to L. Means this is a maximum point, and when this is a maximum point, means the path difference. This means that path difference at this point L is 0. Okay. Now moving on to Q, they say that Q is at Q it's a minimum loudness. So I'll write over here the path difference over here between the waves is now half of the wavelength of the sound wave. Now again, L is a maximum point, so I'll write over here path difference. Basically path difference is nothing but extra distance traveled by the sound wave from some source. So path difference over here will be equal to one wavelength, and again Q is a minimum loudness, is at minimum loudness. So over here the path difference at this point will be equal to 3/2 of the wavelength of the sound wave. And again over here, path difference at this L, or path difference at this L, is 2 into wavelength. Means a sound wave from S2 is just traveling 7.4 meters to reach point Y, but sound wave from S1 will be traveling 7.4 plus 2 times of its wavelength extra. So the extra distance it is traveling is path difference, which is 2 times of its wavelength. So our answer will be S1Y. Our answer will be equal to 7.4 plus 2 times of the wavelength of the wave, so which is 0.85, and it is mentioned in the question. So this becomes 9.1 meters. Question 6. A battery of electromotive force EMF E and internal resistance R is connected to a variable resistor of resistance R as shown in figure 6.1. So this is a complete circuit. Over here that's a variable resistor with the voltage V. A current of I is a current is gonna move across the circuit, and it is having an EMF of E, and it also has, the battery also has an internal resistance of value R, small r. The current in the circuit is I and the potential difference across the variable resistors is V. Part A, explain in terms of energy why V is less than E. Of course, it is not possible that each volt which is being produced by the EMF will be consumed by the variable resistor over here. It won't be able to do that because some of the volts might be lost in its own internal resistance. The battery might be losing some of the volts and will be outputting some other volts. So it is never possible for the battery to output its whole energy out. So, and this is what they are asking you to explain why it cannot do so. So the answer would be some energy is lost in the form of heat by internal resistance of the battery. Okay. Okay. Part B, state an equation relating E, I, R, and V. Okay. So the total EMF which is applied to the circuit is equal to voltage across the resistor or across any component which is attached into the circuit plus the energy lost in internal resistance of the battery. Part C, the resistance R of the variable resistor is varied. The variation with current of voltage is shown in figure 6.2. So as the voltage across the resistor is increasing, current across the circuit decreases. That's an inverse relationship. So they are inversely proportional to each other. This means they are inversely proportional to each other over here. Use figure 6.2 to explain how it may be deduced that the EMF of the battery is 2.8 volts. Okay, so from this graph, how can you deduce that the EMF provided by the battery is 2.8 volts exactly? Okay, when we look into the graph, when I is equal to 0 means no volts were lost, and hence PD would be equal to EMF, and at I is equals to 0, voltage or PD is 2.8 volts, hence EMF is 2.8 volts. So what will I write over here? I'll write at I is equal to 0, or when there is no current across the circuit, there are no lost volts. Lost volts are basically volts or energy consumed by the internal resistance, which is usually dissipated in the form of heat. So there are no lost volts, hence EMF is equal to 2.8 volts. Part 2, calculate the internal resistance R. So we'll use this formula. EMF is equals to a potential difference plus lost volts. Our potential difference we already got from part 1, which is 2.8. So 2.8 volts is equals to voltage at any point and then internal resistance at that point within the circuit. Suppose I'll take this value, or I'll take this value of voltage, and accordingly I'll take 0.5 amperes from the graph. So my voltage is 2.1 plus the current I took from the graph is 0.5. R is still unknown to us. When you rearrange the formula, you'll get R is equals to 1.4 ohms. Part D. The battery stores 9.2 kilojoules of energy. The variable resistor is adjusted so that V is equals to 2.1 volts. Use figure 6.2 to calculate resistance R. Now we have to make use of the graph to calculate resistance R. So at 2.1 volts, you see, at 2.1 volts, we have 0.5 amperes of current. So formula for resistance is voltage divided by current. In our taken values, in our question, we are being given 2.1 volts divided by 0.5 amperes, and our answer for resistance is equal to 4.2 ohms. Part 2, calculate the number of conduction electrons moving through the battery in a time of 1 second. Okay, so the formula I'll be using over here will be is total charge is equal to number of electrons multiplied by charge of 1 electron, which is a fixed value. So this total charge we can calculate with the help of the equation current into time. Current is 0.5 amperes when the voltage has been adjusted to 2.1. So 0.5 comes from the graph at 2.1 volts. 0.5 into time, it is equal to 1. So 1 is equal to number of electrons is still unknown to us. We will leave it as x multiplied by, or I'll write it, electrons multiplied by charge of 1 electrons, which is a fixed value, and that is 1.6 into 10 to the power minus 19. So number of electrons are 3.1 into 10 to the power 18. These much of electrons we have over here. Part 3, determine the time taken for the energy in the battery to become equal to 1.6 kilojoules. So they're asking us how long will it take to reduce the energy of the battery from 9.2 kilojoules to 1.6 kilojoules. So the formula I'll be using over here is energy is equal to voltage into current into time. Time is what we have to calculate. Energy, the change in energy is 9200 joules minus 1600 joules, and 1600 comes from here. I converted kilojoules to joules, making it to SI unit, so this becomes 1600 joules is equal to voltage. They say assume that the EMF of the battery and the current in the battery remain constant. So our EMF is 2.8 into current is 0.5 into time is what we have been asked for. So time is equal to 5.4 into 10 to the power 3 seconds. Now moving on to the last question, 7a. One of the results of the alpha particles scattering experiment is that a very small minority of the alpha particles are scattered through angles greater than 90 degrees. State what may be inferred from about the structure of the atom from this result. So since the marks allocated to this part of the question is so we must mention two things. Firstly, it is said that it scatters means repulsion takes place, and repulsion takes place only when same charges come before each other. So this is deduced that nucleus is positively charged. It is a charged particle and it is positively charged, and most of the mass of the atom is concentrated into nucleus. That's what scatters. So I'll write over here, nucleus is positively charged. Nucleus of the atom is positively charged, and also most mass of the atom is concentrated into its nucleus. First, look for the marks which are allocated to each question, and then according to that you have to mention the points. Part B. A hadron has an overall charge of plus E, where E is the elementary charge. The hadron contains 3 quarks. One of the quarks is a strange quark. Part 1. State the charge in terms of E of the strange quark. So a charge is fixed for all the quarks. For strange quark specifically, this is -1/3 E. That's the fixed charge for a strange quark. Part 2, the other 2 quarks in the hadron have the same charge as each other. By considering charges, determine a possible type of the other 2 quarks. Explain your working. So in the question earlier, they mentioned that a hadron has an overall charge of positive E, means +1. So, and it contains only 3 quarks. The first quark has a charge of -1/3. The other quarks, they share the same charges, and the total charge of the hadron is +1. So I'll write it over here. The first quark has a -1/3 plus some quark, and then the same quark will add up their charges, and this is equal to 1. When I rearrange this, I'll get 2x. Both are x because in the question it says they both share the same charges. It means they both are the same, either the same quarks, or it's just that they share the same charges. So 2x is equals to 4/3. So the value of x is 2/3. Means both the quarks share 2/3 charge, and the quark is an up quark, and up quark has a charge of positive 2/3. So there are 2 up quarks. Yes. So this is the end of the paper. We are done with May-June 2019 paper 2 variant 1.